All right, in this video, we're going to talk a little bit about the collective behavior of objects when they are moving around a center. And just like we did with kinetic energy, where we were working with the total kinetic energy and breaking that down into a translational bit and a rotational bit, we're going to break angular momentum down into a translational bit and a rotational bit, where the translational bit has to do with what we talked about in the video previously, or in the previous video, where an object is moving past a location. And the rotational bit has to do with a set of objects collectively rotating about an axis. So let's take an example where we only have rotational angular momentum. So I'm going to take a disk here, and I'm going to allow this disk to rotate with an angular velocity omega, or an angular speed omega right now. And it rotates about its center. And we're going to consider an atom sitting right here, which is a distance r perpendicular away, and it moves with a momentum p. And we're going to calculate what the angular momentum of that atom is. So I'm going to go ahead and get rid of this stuff over here, because we know what we're trying to achieve. So the magnitude of the angular momentum of that atom is simply the product of r perpendicular times p. The reason is that these two vectors are perpendicular to each other, so we don't have to worry about the sign of the angle. Now, what is the momentum of this atom? Momentum of the atom is going to be the mass of the atom times its velocity. It's linear velocity at this location. Now, if the whole disk rotates with an angular speed omega, then that velocity is known to us as r perpendicular times omega. And so what we have is an angular momentum of the atom, which is equal to r perpendicular times the mass of the atom times r perpendicular times omega, which we can rewrite as the mass of the atom times r perpendicular squared times omega. Now that's a very nice way of writing it, because if you remember, this thing right here looks like a moment of inertia. It's a mass times a distance squared. And it turns out that that's the moment of inertia of this atom at a distance r perpendicular from the center. So in fact, what we have is a description of the angular momentum of this atom, which is that it is the moment of inertia of the atom times omega. Well, that's very nice, because we can think about adding up all the atoms in the disk, right? And so if we add up all the atoms in the disk, we're going to have different r perpendiculars for each one. They're all going to have the same mass. They're all going to have the same omega. And so when we want to calculate the total rotational angular momentum associated with this, we're going to end up calculating the sum on all the atoms times omega, which would just give us I of whatever the object is. In this case, it's a disk, times omega. So we have a definition for the angular momentum, the rotational angular momentum associated with the collective motion of objects around a center, which is that the rotational angular momentum, its magnitude, is I times omega. Well, but we know that this angular momentum is a vector. Well, the moment of inertia is a scalar quantity. It's the value that an object takes on. It's how easy it is to rotate an object. So it must be that this thing that we've been calling the angular speed, or the angular velocity sort of interchangeably, is actually a velocity. It's a velocity vector. And so when you have an object that rotates around like this, it must be that the angular momentum vector and the angular velocity vector point in the same direction. So we're going to introduce another right-hand rule, which is if you curl your fingers around the direction in which something is rotating like this, it'll give you a sense of what that angular momentum is going to be. The angular momentum of this system is out of the board. And therefore, omega, the angular velocity, is also out of the board. So we have two types of right-hand rules that we've been working with, is the r cross p, which tells us about the angular momentum translational by curling our fingers. But then there's this sort of curly one where we follow the way something is rotating, and our thumb tells us the direction of the angular momentum vector in that sense. So this is what we're going to work with when we're talking about objects that rotate about their centers. R cross P is what we'll talk about when objects are translating. Sometimes you will have an object that is both translating and rotating, and you'll have to deal with both of those situations. So our total angular momentum in this case, let's get rid of some of this stuff. The way that we're going to describe the total angular momentum will be that the total angular momentum is the translational plus the rotational. And this is going to be equal to R cross the momentum of the center of mass. So you're watching how the object itself moves with respect to some position. And to that we will add I times omega, which is how the object rotates about its own center. So this is how we will describe the total angular momentum for systems where we have both rotational and translational bits of our angular momentum.